logic gate interfacing, and also encoder. Encoder, what we learned previously is to encode some signal. So this one just like a password, your ATM PIN number. So you key in decimal from 0 to 9, and then it has a binary conversion, a converter decimal, and then the signal will go in the circuit and produce alpha, beta, theta, mu. So in this question, you as a member in R&D unit, you have been assigned to finish pending project. This is pending project to design a new type of encoder. The first prototype shown in figure 8. Jadi this encoder will convert signal from decimal into 4 binary number A, B, theta, alpha, beta, theta, mu. However, this prototype do not produce a unique output for each particular decimal. What is mean by unique output? What is mean by unique output? So have you screenshot this one or not? Done, okay. So what is mean by unique output? Nobody want try to answer? The number one or output out. Okay, unique output mean that if we put 0 to 9, from each 0 to 9, alpha, beta, theta, and mu will produce different configuration. So that what we call encode. So let's say you key in number 2. Suddenly number 2 after go into that circuit, it produce 1001, for example. And then when you key in 7, the 7 also produce 1001. Mean that the receiver, the one that receive, try to decode that code signal. So how can he distinguish this 1001 is represent number 2 or number 7? Because there is no unique. So each input shall have unique output, mean that only one output correspond to each input. So that what we call unique. Okay. So based on that, okay, so what you need to do from that particular what we call particular circuit just now, try to when we input 0 to 9, the binary converter decimal will produce will convert this decimal to binary, and then this binary we'll go to each component. We go to each component and then try to get what is the output coming out correspond to each combination decimal here. So from this decimal input, what will be the combination of the first prototype output? Okay, but it already in this question I already give that it should it not produce unique. Okay, so try to get this one first. Try to get it, and this one just exercise for you. Exercise for you, and then uh, and then try to do suggestion on what modification in order to get unique to get better version of the encoder. Mean that each particular decimal will produce unique alpha, beta, theta, mu combination. Okay, and then from that, try to put in the value here. And to make your life easy, maybe you need to add one more column, the equivalent value for decimal. Okay, so try to okay, this one maybe you just take the bottom one, also same. So first try to figure out what is from the first circuit, try to get the output from the first version, and then try make modification on the circuit and try to get the output from your modified prototype. Better you do this exercise for your for your own good. Okay. Okay. And here for the exercise. Okay. Modification you can totally make new circuit, but please do include what we call for your exercise. You can include at least one relay. In this relay, let's say B is 0. When B is 0, the 0 voltage go to the base of transistor, so the transistor will not on. So when the transistor is not on, so no current will energize the relay. Okay. So the arm of the relay will be at this location in what we call one. This one will be contact to this line. This one is 12 volt. So you imagine 12 volt go inside this one. 12 volt high. This is N, so you get high here. So when you get high here, so it go to this one. The transistor will on. However, you want to get the output beta, so you need to check the above one. So above one now is contact with ground. So no current will flow. So beta still 0 unless beta is connected to 12 volt. Mean that this one is on. Let's say you have combination 0, 1. A is 0. This one C is 1. And then 0, 1 is 0. This is none. You get high. High go to the transistor. Transistor is on. 12 volt come pass here. And then this one will produce high because you have another resistance here. So it you have high mu, and then this one energized, and then the relay is on. The relay is on. This arm will be contacted to 12 volt. 12 volt will pass through the diode, the transistor, and beta will on in case that what we call B is off. B is off. So try to key in each of the number ABC and try to get this value first. I do advise, please do it. Please do it. Okay. Now we're going to continue on encoding and decoding. So this one is we will go very fast. We just want to get idea on what is mean by encode and decode. BCD stand for binary coded decimal. We have, let's say we have a decimal number, and then we can make a conversion to this value, okay, by using BCD IC. So nowadays you don't need to use, if you being asked to do a conversion, code is different with conversion. Mean that this one just give direct translate from 4 to decimal, 9 to decimal, 9 to binary, 4 to binary, 2 to binary. But does it represent the value of 4,926 or not? And then that one you need to convert using a calculator. Okay. So BCD is the IC or circuit to encode binary to decimal to binary to decimal. Okay. Also we have that one encode IC, and then we also have decode IC. IC we have binary, we want to decode to decimal again. And then after the first code they make from binary to decimal, they introduce another code, exit3 code. Exit3 code. In exit3 code, each value of binary after convert from decimal, they just add 3. They just add 3. Okay. Why they add 3? Because they don't want others to know their what we call their code. So this one is really if you watch several movie related to to encode or secret coding, the first movie that suggested to understand the concept is Wind Talker. And in that movie, it is a war between US and Japan in Hawaii. I think in Hawaii Island during that time, so quite a number of Japanese understand English language. So US Army have problem because their intelligence always being intercepted by Japanese through radio frequency. So they think they should now change the way to encode the information. So what US did, they recruit quite a number of Red Indian people to become their army, and then these Red Indian will become their intelligent in terms of converting the code to send to other team. So when they do Morse code in sending the information, and when the Japanese army intercept their RF radio frequency, and then they have difficulty in terms of interpreting because Japanese army they never learn Red Indian. So that coding stand helping US Army for I think around almost 30 years. 30 years. Uh, After that, when computer comes, uh, if you watch another movie related to computer, that one, I think Enigma. I think maybe some of you, the man that first built computer during World War I between German and UK that time. Uh, so German have their own encoder system named Enigma, if I'm not wrong. So they have a very big problem in how to decode that Enigma code, to decode Enigma code due to first in German language, and then second one it is a mix of several other what we call symbol like uh, bracket, a slash, punctuation mark, so like that. So they take quite long time. So finally, after the first computer built up, and then they successfully able to decode Enigma coding from German, and then they can intercept each German intelligent information. So that is the the way how how they do encode and decode. Same like your password in, let's say, in your Gmail or your Facebook. Uh, Same, also crypto. I think the the name for that one is cryptography. If not, cryptography is the field that use physics and mathematics to to encode and decode some information to make sure it's not easily being break. So when you make password, that's why in term of password, they advise you not to put 1 2 3 4 5 6, because that one is very easy to crack. So they say put capital letter, put small letter, put at least one symbol, include number and everything. So when you put, for example, 1 2 3 4, the this number actually is not sent as 1 2 3 4 to your Gmail server, but it's already converted to another form, and then Gmail has own decode to decode again that encoded password, and then match with your own password. So now they make a cryptocurrency because they think that cryptocurrency is impossible to break. But last 3 days news mentioned that cryptocurrency have been stolen by someone, and then they already lost around 400 or 300 bit Bitcoin. So the loss is around, I think 300 like that. They lost around 30 million USD, something like that. So meaning that any any code, there are still a person who like to decode it. Even though now they may think, because you learn physics, they say that they want to do quantum security using quantum computing, because it is very difficult to crack photon information. Now they say, can we bring our own fiber optic with this fiber optic made by slow light material, and then you bring your information in terms of light, and then you go to your computer, plug in this fiber optic, and then when the light is go inside your computer, each light have their own phase, their own intensity, their own polarization. So from that information, your what we call your your data is more safe. However, last time I also read on some article on, if we send a data in terms of light, and then someone have stole one of the photon, can we guess what is the photon that lost looks like? Actually, they can, they still have high chances to guess the lost photon. So in that discussion, they said, even though we send in terms of photon, and if you able to steal some of the photon, not all, you still can guess the information. For example, if we have the word B here, the word B here. Let's say we make it bigger. The concept is quite, I think, quite easy. So it say, let's say this B is represented by 6 photon. So this part 1, 2, and half of this B, 3, 4, 5, 6. So he said, if we have a square mean that the stolen photon, that uh, okay. So let's say we have this one. See. So let's say we have two of the photon has been stolen. Two of the photon has been stolen, and then uh, can we still crack the information, the idea in the discussion? So from this one, you only have 3 possibility of word. Either it is B, or I think 2. It is B or R. So you have just two, even though your photon, this guy just able to select 4 or 5. Based on that, they can still guess the word, the word that able to be solved by this one. And then if this guy only observe the top part and the lower part, and then what they said, they said if that is the cases, so like this, and then this one, because we just they just be able to select like that. Okay. in this case, when you get this information, you may think, oh, this one possibly if drag here, we get even D, and then we may get P. No other possible word. So it is between B and D. So you still can guess because only two probability to guess. So based on the statistic, they say still possible to guess what type of the full information of this from the stolen photon. So that just a discussion or sharing. So this one is XC3 code. Okay, and then we have gray code. Okay, gray code just to show the increment associate to the input or output of the optical devices of a shaft angular position. Yeah, it's not showing the real number, but it's just showing the increment of the, let's say we have one disc, optical disc, and then each of the step they have increment, mean that from the position 0, 0, 0, 0 degree, and then each step. So this one it have I think I don't remember how many step, around 64 step maybe, or 32 step. So so from that you can guess, you can know the position based on the gray code. Okay, so the gray code is not used to assign for binary value or decimal value. It just to show the position, whether it's increment count or decrement count of the optical encoder or shaft positioning. So we have ASCII code. ASCII code is the one that we will use in computer when you get data file from the raw PC, raw instrument. Normally we save it in TXT or ASCII or DAT or in CSV, so that we can use this information, the file, and can be open in almost most of the software. And then it represent number, letter, punctuation mark, and control character. This one just knowledge. So we have electronic encoder, the one that I show in the example in the beginning of the class. This one is to convert from decimal to binary. So this one is decimal to binary encoder. So from the decimal, we key in we press the button, and then the binary will become increasing. Show the binary value equivalent to this decimal input. Okay, so it's available in IC form. And then from this one, we have another one that you use in your year 2 is like emitting diode based on 7-segment display. Also, we have two type, one LED based, one LCD based. This one LED use high power consumption. That's why your handphone use quite a lot of battery power compared to your last Nokia phone. And then LCD mostly used in calculator. That's why your calculator never change the battery for even 3 or 4 years, because LCD display use very what you call, very low power consumption. It's good to view only good in good light. Mean that we never use calculator in the dark room, because the character going to be dark is appear. However, we need to use in the bright environment. However, for LED type, if the outside is too bright, it's very difficult to see the screen. That's why under very under very under midday, when you want to see your phone, you need to do like that in the midday. And then we have vacuum display. This one is based on cathode ray tube. Okay. Okay, this one you do it in your year 2. We have limiting resistance, and then you what we call you ground each pin. After you ground each pin, the display, the 7-segment display will appear will display the number that correspond to the leg of the pin that you grounded. Okay. Okay. Okay, for crystal display, I'm not going. You can read by your own. But this one is just information how it's work. Yeah. Okay, so the most important topic, information or topic in this chapter is the definition of encode and decode. So encode mean that you have one raw data that you understand, and then you want to change to binary or any other code. If you just use BCD, you can have direct conversion from the decimal to binary, and then you can add some more value, just like exit recode, to change your initial encode value. And then we have a gray code to represent increment and decrement, and ASCII code, ASCII code that used in computer. And then we'll also learn about the decimal to binary encoded IC that can attach directly to the 7-segment display. Okay, so that is idea. Encode, you have normal information, you change to some other coding, and then the decoder, that coding or that code, you undo it again to become information that you present, that you understand when you read. Okay, you or display to you. Okay, now we are going to the flip-flop. So this one is very straightforward. Very straightforward. You need to what we call. You also need to remember on the truth table. Okay. First, we have two type of logic circuit. Now the first one is conventional logic circuit. This one is from the basic building block, that like inverter, AND gate, NOR gate, NAND gate, NOR gate, like that. And then we can make any of the gate by our own arrangement for specific purpose, for certain purpose that we can custom it. Just like in the first example in the beginning of the class, so that one is using conventional logic gate. And then the second one, we have sequential logic gate. Sequential logic gate is basic building block include the flip-flop. Okay, so we have several example here is RS flip-flop, and then we have D flip-flop, we have JK flip-flop, and also we have also clock RS flip-flop. So what is RS flip-flop? RS flip-flop is the IC, one IC inside that circuit, flip-flop circuit. It has two NAND gates with two input R and S, set and reset. And also we have the output Q, normal, and complementary Q bar. And then this NAND gate is connected by the output of the first. The first will become the input for the second NAND gate, and the output of the second NAND gate will become input of the first NAND gate. So the truth table for this flip-flop is present by this this table. And so we have four state here. Four state. First we have prohibited state. Okay, because we know this one is normal, we have Q and Q bar, mean that it should, if Q equal to 1, Q bar will become 0. Q bar will become 0. That's what we call complementary. So in the prohibited mode, if we put 0, 0 at S and R, the output will become 1 and 1. So this one is prohibited. Okay, prohibited mean that if you put 0, 0, does not make you get seen. Okay, but we cannot use because we cannot differentiate between Q and Q bar because both give us the same value. Okay, both give us the same value. So that's why it's called prohibited. So we never run our flip-flop in the condition that S and R is 0, 0. Okay, because the output will give the same value, so we cannot distinguish the output. Okay, but if we put 0, 0, the flip-flop not damaged. It's not damaged. It just gives the output 1, 1. Okay, and then we have a set condition, set mode, where the output of S is 0, input of S is 0, input of R is 1. So you will get output here Q equal 1 and Q prime 0. So normally you just need to remember the Q output, because Q prime should be Q prime should be opposite of the Q. Okay, based on that, if you see S, when we give set value is 0, Q will become 1, and when in the reset condition, S is 1, Q will become 0, R is 0, and then Q will become 0. And then in the whole position, it means that the Q will remain the same from the previous Q, is we give both 0, 0, 1, 1, 1, 1. So when you give 0 to S and Q become 1, this one is noted as active low input. So in the symbol, we know it is active low if we have this circle like that. The circle like that, this is active low symbol, mean that if we give 0, it become 1 inside. So Q will become 1. So that is active 0. Active 0 just like a NOT gate at the beginning of the flip-flop. Okay, but we not need to put the NOT gate, but the behavior of the flip-flop itself, it will have active low. So let's have some example. If we give S low, R high, what should be the output? And what is the operation, mode of operation? Ada orang tak? Anybody in the room? Wah, sikitnya orang datang hari ni. Shang, how about you? You have any idea? Apa yang ramai tak datang kelas ni? Emeline. Emeline, oh Emeline. Ui, ada depan ni tak? So the output queue will be high and the operation, what is operation, Shang? So operation is set. So the output is high. Just look for the queue. Just look for the queue because we know the Q prime will be opposite. So what happened when we from the state we give high. So the operation is hold and then the Q remain high because it hold the previous output. And then we make high low and then the operation will be reset and low. Okay. After that, we have extension in terms of from RS flip-flop, we have clock RS flip-flop. So the clock RS flip-flop, they add two more NAND gate here. And then we have one clock. Clock mean that digital path with either fixed frequency or based on trigger. Okay, sometimes based on trigger, sometimes based on fixed frequency. Okay, we have the symbol like flip flop for clock RS like this one. However, if you notice in the input here there are no circle. This is direct straight line. Mean that it is active high input. So when active high mean that it just opposite with the previous flip flop. Just follow S. When you give 0, 0, 0 is no change, we can hold. If set is 1, Q become 1. And if set is 0, Q becomes 0. So the prohibited mode is 1, 1. And then the first three will only active when the clock is coming. You get positive clock, mean that you get square like that, and then the output will be changed. If no clock given, you just change 0, 0, 0, 1, 1, 0, but you not put any clock, no pulse coming, so you will get no change in the output. This one clock mean it's only active when you give clock to the to the input. Okay. So this one you can try to remember the table, but for our final it is open book final, or so you want to open your book, you want to open your laptop also can, but you cannot make a discussion even at the pasar. Okay, so the mode of operation. This one is represent the clock is positive pulse. it go high. Okay. So when we S high and R low, we have positive clock. We are in the set mode, we get high output. And then if low, we get hold mode, and then the result is still high, carry from the previous. And then when S is low, R is high, we have clock, mode is reset, it become low again. Okay, so we already have two type of flip-flop, one RS flip-flop and clock RS flip-flop. And then we have D flip-flop. D flip-flop is much a bit complicated to what we call to JK flip-flop because it have preset and clear input. Okay, preset and clear input. Okay, so if the easiest way to understand is if we preset, so when any of preset and clear input is zero, so clock and the input is irrelevant. It just directly follow from the input of the clock preset and clear. So because preset and clear is active low, however the others is active high. Okay, active high mean that if preset given 0, Q will become 1, and this one is as asynchronous set, and asynchronous reset is preset 1 clear 0, and then Q become Q naught. Okay, a moment. Okay, so when the preset and clear have the value 1, and then we start to see the clock input and the input, and then we will have the output Q based on the table. Okay, remember here for the clock, it show us what we call that arrow to the top. This one represent a low to high transition clock, mean that the symbol in the diagram will become more than. Uh, we have square clock. So the output will be activated, will be changed when they have positive slope. Positive slope that during the first transition, you have the edge, increment edge, and then the output changes. Okay, that's what we call low to high transition clock pulse. Okay, and then when the clock coming down, no changes at the output, but when the second clock is coming, and then you start to have the rise up time, and then the output will be correspond to the clock and the D input. So this one is in D flip-flop. So now preset low, clear high. So in asynchronous set, the output will be high. No need to see, no need to aware on the clock and the input. And then now we have both high. What is the condition? When both high, mean that it's not based on the synchronized or asynchronized. So now we will see what is the D and clock. So now we have D low, so the output will be reset, and then the mode operation is reset, and then the output will be low. And then we have high again, and D is high, and we have clock. So Q will be based on D is active high. So we'll get in set value, set mode and high output. High mean let's say 12 volt, 5 volt, or any volt based on the IC datasheet. Finally, we have JK flip-flop. Okay, JK flip-flop, it's a bit different from D flip-flop. It have 3 input, J, K, and clock. For D, it only have D and clock. Okay. However, for JK flip-flop here, if you note that at the clock input, they have one circle. One circle. That circle represent transition to high to low. Mean that your clock is coming up, and then when it going down, then the output will be changed during that time. If your clock is very long, let's say 1 second, but not yet coming down, so the output will not change. Mean that like you press something, you press the switch, after you release and then it responds. In some cases, when you press the switch, even though you're not released yet, the output already changed. Okay. For example, in the door, normally when you press, it just open the door. Okay. However, for the lift, when you press the door, when you release the door, and then the door is closed. Okay, so that is different. Lift door and normal door at shopping complex. Kejap nak habis lah. Okay. So in JK flip-flop, they have another function toggle. Toggle just to flip the output to opposite the output. If the output previously high and it become low, and if previously low, it become high. So normal JK flip-flop is very useful in terms of toggling function. So do remember that when any of preset and clear have the value 0, JK and clock is irrelevant. Irrelevant means you not need to observe this one. Directly give the Q output based on that. Okay. And then also do remember the symbol at the clock, whether it is active high or active low. Not active high or active low, is whether it is positive edge or negative edge transition. Okay. So so that one, I think you can have the what we call the example here in the slide that I have shared the slide or not. I not remember on that. And then also you can read on the textbook. Okay. So latch fundamental digital storage device. It act of store data for a time such as to latch. RS flip-flop is example of latch. Mean that as long as no new input, the output still remain there. Okay. D flip-flop also have that capability. So it is in IC form, we can have in 4-bit, 8-bit, 9-bit, 10-bit. Commonly, it is embedded in the complex IC form. Okay, now how to trigger flip-flop? Okay, just now we have level triggering. Level triggering is transfer data from input to output flip-flop anytime when the clock is high. So when the clock's at high, and then it just transfer the output. Mean that level triggering refer to this part. This one is level triggering. It not look for this one. As long as the high value achieve the amount of voltage needed, so it will respond. However, for edge triggering, this one we call positive edge triggering from low to high. So you just have more than symbol. And then we have another one, negative age triggering. So it just responds when triggering the level transit from high to low, and the symbol have more than symbol with the circle, whether inside or at the side. Okay, so flip-flop on the low to high transition, we name it as positive age trigger device. If high to low, negative age trigger device. And then trigger while clock pulse is high. We say it is level trigger device. And then we have Smith trigger operation. Smith trigger operation. Smith trigger is to change the analog signal to digital signal, and then we can set the we can set the what we call the positive going threshold and negative going threshold in order to change the signal, whether it's high pulse or low pulse. So let's say we have sine wave here, and then the sine wave is go to the input. This one is just like Smith trigger with the not output. I mean it convert. So invert the input. So here is high. You have not, it become low, and then this one is low. Anyone lower than this triggering negative going threshold, it become high. Okay, so this one is inverter. So when the sine wave signal goes into the Smith trigger operation, so it will change the sine wave to digital pulse, depending on the width of the digital pulse depend on the positive going trigger or negative going trigger uh, that 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 given to this one. However, it only based on the first high level detector here. So as long as high, the first one high, and then changes, as long as the changes not go lower than negative going threshold, it will remain low until it is lower. The output is lower. The input is lower than the negative going threshold. So like that. Okay. So it make us easier. And then this one, from this one, where can we use this one? We can use in terms of producing clock. Let's say the clock is the clock is in the sine wave oscillation from the any oscillator, natural oscillator. So we want to make sure the clock becomes square. We can use Smith trigger operation in order to change the clock from analog to square, the digital signal, digital clock. So please read on the RS and JK flip flop from the textbook, because that going to be your what we call your test to what we call test to question. I will giving you the input in terms of wave, and then when wave will go to the each input position of PS, PS, clear, JK, and clock. What will be the output at the Q and Q bar? It's for that one for JK. Uh, uh, I give the information. The question will be in the signal form, not a numbering. So you will need to draw the output signal. Okay, that's all. Please try do some exercise in the textbook to familiarize and then do remember.